Right. So, hi. Thank you, Raghu. Thank you, Koushik. Thank you, Subinoy. I think Vikram isn't here, but thank you, Vikram Rentala as well, for inviting me to give this talk. It's always a pleasure to give talks at ICTS. It's always impeccably organized, and then with such fantastic organizers of the workshop, everything is supposed to work perfectly, and it has so far. So. It's wonderful. It's also wonderful to see so many people at 9:30 in the morning. Unlike perhaps many of you guys, I don't wake up at 9:30. I just managed to get my coffee. So hopefully I'll not make too many blunders today. Okay, so this workshop is about less traveled paths on dark matter, right? Less traveled paths on dark matter. But my talk is about the more traveled part of those less traveled paths in some sense. So I'll talk about things that are fairly standard, things that more or less everyone agrees on, very little, let's say, uncertainty, at least the first maybe even both lectures. I would say that I would not be talking about things that are in any way unknown. Everyone knows these things in the field. So these are like what we would call standard lore. The later lectures, so for example, Neil Weiner will introduce to you about more modern and recently developed models. Other lecturers will tell you about axions, primordial black holes, other things. My lecture will be largely focused on first telling you why we believe there is dark matter. Okay, so that's the first thing. That how do we know that there is something called dark matter? And then I will try to give you some very basic introduction to cosmology, which will allow us to discuss the most frequently discussed method for how dark matter could have formed. So the production of dark matter in the early universe. So that's called the freeze out paradigm or thermal freeze out paradigm. So we will discuss that. And then we will move on to other cosmological probes of dark matter. So essentially we will ask, even if we don't know about any of the properties of dark matter, the detailed properties of dark matter. Let's say we don't know its, which interactions it has. Does it interact more with the top quark or the neutrino or say something else? Even if we don't know these details, what can we learn about dark matter from cosmological observations? So that's roughly the plan of the talk. That first I'll give you the evidence. Then I'll give you some introduction to basic cosmology needed to discuss dark matter. Then I'll talk about freeze out, and then finally probes of dark matter properties, particle properties of dark matter, using essentially large-scale structure. Okay. All right, I hear a bunch of birds chirping, and normally I would love them, but if you don't mind, please mute your microphones. That'll help all of us. Okay. Right, so let me start in a minute. Okay, now this is a picture that most of you would be familiar with. This is a picture taken from space of India, and there are these lights that you see. These are not at Diwali, just usual street lights, most of them. And if I ask any of you, that, okay, what's going on in those regions which are dark? Nobody in their right mind would ever say that, okay, it's just a vacuum out there. There is no land, there is no water, there's nothing. It's just empty space there. We don't say that because our intuition is already attuned. We know that the light tracks the number of people in this map, if you will. And the dark areas just tell us that there are no people there, but that doesn't mean that there's nothing there. Compare this intuition to the next picture that I'm about to show you. Okay. Now, this is not a real image. This is something that's made on a computer. It's what is called an n-body simulation. I'll tell you a little bit more about it tomorrow. But this is what our universe looks on the largest scales. So the scale is given to you. It's 100 million light years across this box. And the yellow dots that you see, these are galaxies and galaxy clusters. Clusters of galaxies are called galaxy clusters. And you can see filaments and sheets of galaxies and galaxy clusters forming structure. And then there are voids in between which are very dark. But if someone were to be asked that what's going on, let's say in this region, which is supposedly reasonably dark, is what's going on there? Like let's say this region, there's no light there. Is it empty? And often at least for the longest time, the intuition that even let's say well-known astronomers would have had is that okay, that part of the space is completely empty. But that's not really true. There is a diffuse kind of matter that's pervading all of space, in the entire universe that we can observe. And our visible galaxies are embedded like, cherries in a cake inside this diffuse gas. So this is an artist's impression. This is roughly what a galaxy looks like. So this galaxy is about 100,000 light years across, but it comes embedded in this hazy cloud called a halo of dark matter. So to keep numbers in mind, the galaxy itself is about 100,000 light years. If you are more familiar with kiloparsecs, so the galaxy is about 10 kiloparsecs. And then the dark matter halo is approximately a factor of 10 to 50 larger. Okay. Now this density of this dark matter in this halo is not a constant. We will learn what it looks like. But first, I wanted all of you to have a visual picture of what dark matter looks. If you could see dark matter, what it would look like. This is what it would look like. Okay. Okay. So now coming to the meat of our talk today. Two questions we want to answer today. How do we know that dark matter exists and what is it? Okay. So the first one I will give you, I think, very convincing answers. You can tell me if you disagree later. And the second one, I will not be able to tell you what dark matter is because that's not known. And that's what we are all trying to work out. And that's an exciting thing. You have an opportunity, therefore, to take part in this endeavor and contribute to finding out the answer to this very exciting question. The key idea that will be used to figuring out why there must be something like dark matter is that motion of objects is related to the mass of other objects that influence the motion of the said test object. Okay, so the simple example that I could give you is that you drop an apple, it takes approximately a second to fall, let's say the height of 1 meter or so. And from that, you can compute the mass of Earth if you know the acceleration due to gravity. And this is something that you've all done in school. Now, somewhat more, not particularly more sophisticated versions of this idea are used to infer that there is dark matter in the universe. And dark matter is there at many different scales. You can see that there is dark matter in galaxies, there is dark matter in clusters of galaxies, about 1,000 galaxies, stuck together in this big cloud called a cluster. There's dark matter at the level of our horizon. So in all these scales, there is evidence for dark matter, and I'll tell you about it in a second. But in all these cases, the key idea is that you use some form of this F equal to ma equation to find out the acceleration of a test particle, and the acceleration depends on the mass that is causing the acceleration. This is the trick. We always use gravitational force of the dark matter on some test particle to know that there is dark matter. That's the central idea. Okay? So let's look at the evidence roughly in chronological order. So the first evidence that we had that there was something like dark matter came from observations of clusters of galaxies. So clusters of galaxies, as I just told you, about 1,000 galaxies stuck together in a nebula, they used to be called. At that time, people didn't know that there are things like galaxies and they're outside our galaxy. So these were very early times, 1930s. I'm talking about. But this gas of galaxies, very similar to what you have perhaps seen in your undergraduate course as a gas of particles, you can use the virial theorem that the average kinetic energy is related to the potential energy. Okay? So this is what this equation says, that half mv square, the average basically tells you that it's some sort of a average over an ensemble, and that is equal to minus gmm by 2r. Sorry, the minus sign should have gone away. Fix now. Okay, and I can cross out the mass of the test particle from this equation, and then I can write an equation for this capital M, which is the mass of the galaxy itself, which is causing this velocity dispersion. So the mass of the cluster, if you will, mass of the cluster is given by the size of the cluster, R cluster, times the velocity dispersion of the galaxies inside that galaxy cluster, divided by twice the Newton constant. Okay? So that's the formula. Now, how do we measure this mass? The R, the radius of the cluster, can be measured roughly by its physical extent. You see, like, how large is this cluster? G Newton is known, it's a fundamental constant. And V square you measure using Doppler. Doppler shifts of the lines of various spectroscopic lines coming from the light coming from these galaxies. So that's what is shown in this picture here. The two axes are something like the longitude and latitude in skies. It's called right ascension and declination in astro language. And each of the points that you see here is a galaxy in some galaxy cluster. And these galaxies are color coded by their velocity. Okay? So the blue ones are fast. They have approximately 10,000 kilometers per second speeds. And the red ones are somewhat slower. They have approximately 1,000 kilometers per second speed. And if you then now compute the quantity RV square by twice Gn, you'll get some mass. This mass turns out to be something like 10 to the 14 solar masses. The solar masses, the mass of the sun is solar mass, and there's something like 10 to the 14 solar masses. This is to be compared to something like 10 to the 12 solar masses, which is the mass of the Milky Way. Okay? So the cluster is 100 to maybe 1,000 times larger than the mass of a galaxy. But what is more interesting is that you could have counted the total mass in this cluster. You just count the masses of each of the galaxies, count the mass of all the diffuse gas. How it's done, it's a little bit more difficult using mass to light ratios. Let's not go there. But let's say you could count the total mass, and that's what astronomers did. They found that this inferred mass, using this virial theorem argument, was at that time found to be 400 times larger than the mass that you would count by just taking the galaxies and the gas. So clearly there was some mismatch of mass. And then this was called dark matter. So this is from the original paper of Fritz Zwicky, and he uses in the German version of the paper this word Dunkelmaterie, which is dark matter. And basically he says that there's 400 times more matter than you would expect. Okay, so this was the first solid indication that there was a mismatch in the mass that you can see and the mass that you can infer using known laws of physics. This is the first line of evidence, and it comes from clusters of galaxies through dispersion velocities. Okay. So far, so good. Any questions at this point? I can't see the raise hand or anything, so if the moderators could let me know if there are questions, that would be great.
I will keep track, Basu.
Thank you.
There is, okay.
Okay, so let's move on if there are no questions. Oh, Joydeep has raised hand, I can see. But let me know if any questions. Okay, so the second line of evidence for dark matter comes from something called rotation curves. Okay, rotation curves is a very familiar idea that in Newtonian gravity we know that if there is some object like the sun, its satellite, let's say the Earth, goes around in some elliptical orbit, and the velocity of this object that's going around depends on the mass of the sun, which is much heavier. Okay? And the velocity also depends on the distance, of this object from the force center, and it decreases as 1 over square root r. This is Kepler's laws. So in fact, this is very familiar to all of us, that as you go further and further away from the center of force, the linear velocity or orbital velocity in kilometers per second shown here, it decreases, and it decreases as 1 over square root r. This you can simply compute by saying that, well, the force is gmm by r squared, and this must be equal to the centrifugal force, which is mv square over r. And so then you cross this out, and then v square goes as r, and so v goes as 1 over r. Okay, so that's how we know that the velocity should decrease. But this assumes something. What does this assume? That it assumes that all the mass is, this m is contained, at the center, or even if we want to be more general, within the orbit. Newton's this something called shell theorems that tell you is that all the mass which is within the orbit can be thought of as being contained at the center. So even if you use that, it says that this rule works as long as all the mass is contained within the orbit. So this is what is expected, but what is seen for galaxies is somewhat different. So this is again from the original paper by Vera Rubin. So she did this work with her advisor Ken Ford, where they measured Doppler shifts of stars, now not galaxies, stars in the M31 galaxy. And as you look at stars which are further and further away from the center of the galaxy, their orbital velocities don't seem to decrease as 1 over r. Rather, they're more or less flat. You can see this is the distance, this axis, this is the distance from the center of the galaxy. And what you see here, these points, these are practically at the same level. The velocity is not decreasing. Okay, so the velocity does not decrease, and this is a puzzle, why the velocity does not decrease. And the argument is simple. So suppose I use the fact that I use the fact that mass of a test particle times velocity square by the radius at which this test particle exists. This goes roughly like g Newton times mass contained within the orbit times the mass divided by r square. So what I'm saying is that centrifugal force is roughly given by gravity. Then this tells us that v square goes as g m r over r. But we have just found from data that v square is approximately constant. Okay? So what does this allow us to infer? It allows us to infer that the mass contained within a radius r grows like r. Some constant k times r. Then this would be true. So then already we are seeing that as you are going further out from the center of galaxies, the mass is increasing linearly. This is a bit surprising already, because if you see this picture, the galaxy more or less ends here. This is roughly where the extent of this visual part of the galaxy is. But you can see the V square is being constant even outside. So there must be mass outside the visible part of the galaxy. And not only is it there, it is increasing in mass linearly. Okay? Which tells us what? Which tells us that m of r is nothing but integral d3r rho of r, which therefore basically goes as r cube times rho of r, and that is equal to k times r, which basically tells me that rho of r goes as 1 over r squared. So that tells us that there must be matter that's not visible in the galaxy. It extends well beyond the physical extent of the visible part of the galaxy, and it varies with distance from the center as 1 over r squared. Now this is not completely true, we will see, but this is already a very, very close approximation to what goes on in real life. Okay. That was the second evidence for dark matter, rotation curves. The third evidence for dark matter is something that many of you are familiar with. This is the fact that some very massive object will bend light, as it passes by. So, and the amount of bending is proportional to the mass of the object that is causing the bending. Okay. So suppose there is some distant galaxy from which light is coming to Earth, and there is a cluster of galaxies that is in the middle. It acts like a lens and it bends the light, and the amount of bending, which of course can cause multiple images or stretching of images, that will depend on the mass contained in this galaxy cluster. This galaxy cluster has some mass m, and this mass m determines how much bending there is. So let's understand this in a little bit more detail. So this is a picture where this phenomenon is being shown more carefully. What you see, these yellow spots, are galaxies that have been lensed by an intervening object, which let's say is a galaxy cluster. And this white foggy thing is a false color. That is the inferred position and density of mass that is causing the lensing. Where do we see lensing? We see lensing here, for example. You see there is this there is this image here. They have been stretched. Now, of course, galaxies can be elliptical on their own, but you can see that there is some correlation in the way the images have been stretched. For example, there is this, there's this image here which is being stretched, but you can see there are also these images here which have been stretched. So it's very clear that these shears are correlated, and this correlated shear can only happen because there is some mass here which is causing the images to stretch perpendicular to the line joining the lens and the image. So this is lensing that we are seeing. And how much lensing will we see? This is something that you can compute in many different ways, and there are less and more sophisticated ways of doing it. But let's do a simple one. Let's do a simple calculation. So suppose I have a black hole here. And I am looking at light coming from a faraway star. Now, what's going to happen is that light from this star.
Basu,
yes.
There is a question from Siladitya Pore.
Yes.
He asked how this correlation of image is measured.
how this correlation of image is made. At this point, all I request you to focus on in terms of the correlation is the fact that the stretching of this image and the stretching of this image are correlated in what sense? That they are both being stretched in the tangential direction to some circle. So that all these stretched images, they form arcs of some big circles. And the center of the circle is where all the hidden mass is. So all I want to know are two things. Where is the hidden mass and how much mass is there, right? Where is the hidden mass can be found from taking this image, constructing its perpendicular bisector, taking this image, constructing its perpendicular bisector, and finding out that the mass must be roughly there. And you do that for all pairs. How much mass do I put in at this point? This I am now going to answer. Does this answer your question, Shiladitya?
I suggest you go ahead.
Okay. All right. So I'm now going to answer how do we know how much mass to put in? And the answer is very straightforward. Suppose the star is emitting light. If it just emitted light like this in a straight line, it would go. But then as soon as it came close enough to the black hole, it would bend a bit and it would miss my eye. I would not see this. So the light that I see should go like this. Right. So I've not drawn it perfectly, but basically something like this. Okay. And what happens is that the light ray must roughly bend by an angle theta in order to reach the observer. Now let's say the mass of the black hole is mBh. How much is this theta? How much is theta? Suppose I want to know. Well, I know that this theta, whatever it is, must be proportional to the mass of the black hole. Because I could think of this black hole as being composed of two black holes of mass mBh by 2. And nothing should have changed. So theta must depend at least to first order linearly on mBh. Actually, it should depend linearly always. And it should depend on what else? It should depend on the Newton constant. Okay, so we know that it should depend on the Newton constant. And if you use a little bit of dimensional analysis, you will figure out that this distance of closest approach B must go in the denominator. The way to see it is that theta is dimensionless. G Newton has units of 1 over m Planck square in natural units. And B is a distance. So B has dimensions of m inverse, mass inverse. So just to get something dimensionless, this is the only possible answer. Where I'm using the fact very crucially that I know that the bending must be proportional to mass. Okay, the correct answer is in general relativity that there's a factor of 4 here. Okay, this I would not have got out of dimensional analysis. So by looking at the amount of bending, I know how much mass I should put at the center. These two things, like using the correlation between the stretching of the images and how much magnification do I see, these things tell me how much mass is there. That's what has allowed us to create this false color image of the dark matter. Actually, this also contains some cold gas that is not seen, but all the matter that is not seen is then mapped using gravitational lensing. Okay. One of the most spectacular demonstrations of this physics is using something called the bullet cluster. I will tell you a little bit more about it, but this is also these are two galaxy clusters that are colliding and just passing through each other. And here also one sees stretching of certain images. For example, you can see that there are these green lines here. These green lines are contours that contain equal masses. And these have been constructed using gravitational lensing. And the blue hazy color coding tells you how much mass is there at each location. So this is a way to find out where there is mass. Okay, so I have told you so far 3 ways of finding out whether there is dark matter and how much of it is there. Now the fourth way. The fourth way is by looking at some remnants of the Big Bang. So the story is that very early in the universe was very hot and smaller. It is expanding and cooling. So if we are looking back at the universe, if we are looking further and further away, we are looking at a universe that is old, because if you are looking very far away, then light from that far away point can reach us now only if it was emitted long time ago. So when we look at a very far away part of the universe, we are looking at a very old version of that far away universe. Eventually, if we are looking far enough, we are looking at a universe which is so old that it was not neutral, it was ionized, everything was a plasma. And in this older universe, in this part of the universe that I am looking at, light cannot travel in straight lines. Light, if it tries to go, it scatters off other charged particles and it cannot reach us. Only after the universe became neutral, so to say, can light come to me in straight lines like this. So all the light that I see today, at best, comes from this surface. It could be a slightly thickened surface, depending on whether this becoming neutral is instantaneous or it took some time. But roughly speaking, there is no light coming to me, an observer today, that is from behind this last scattering surface. Okay. So, and what does this tell me? That this faraway part of the universe, the one here, this is a plasma. This is a plasma. And so, if it thermalizes, there is some constant density. But any disturbance that you create in that plasma, so suppose there is this plasma and you create a little extra density at some point, this density, because of radiation pressure, will try to go away. But it will go away and it will overshoot, just like a pendulum, and then it will come back. It will flow back into the void, and then this back and forth will continue happening, and it will set up oscillations. These oscillations will therefore set up waves in this plasma. And so even on this last scattering surface, there are density fluctuations. These density fluctuations manifest themselves as temperature fluctuations also. So for example, if this part has higher density, then photons coming from this part of the universe, T, is a bit larger than, let's say, this part of the universe which has a lower density. Let's say this is T low, this is T high. And how are these related? I will tell you a little bit more about it later. But roughly speaking, again, we can use dimensional analysis. We know that energy density rho has dimensions of energy divided by length q. And there is only one scale in the early universe. You can assume that everything is massless relative to the temperature of the universe. So the only scale in the problem is the temperature. So rho must go as T to the power 4. That's the only possible thing to do. And this temperature, therefore, is related to density in this simple way. In fact, there is some prefactor that goes as pi square over 30. And when density is larger, temperature is a bit larger. Okay, so the parts that have larger density have slightly larger temperature, T high, and parts that have smaller density have slightly smaller temperature, T low. And at this point, the universe suddenly froze. That there was the wave could not propagate anymore. And light from these 2 points come to us. And I see the slight inhomogeneities in this large scattering surface as the cosmic microwave background. Okay, so by and large, this is completely uniform. There are at most one part in 10 to the 4 fluctuations of density. So delta rho over rho is roughly, at best, I would say, 10 to the 10 to the minus 4 or so. And this corresponds basically to changes in temperature. You can show this way, up to a factor of 4 or so. So this change in temperature. Now, the point is that the nature of these waves and oscillations depend on two things. It depends on what is the gravitational pull that causes stuff to fall into, the potential well, and how much radiation is there that pushes the photons back and all the matter back to cause this oscillation. If you add more matter which does not interact with light, so to say dark matter, it will lead to larger oscillations, right? So because it will pull very violently and then it will overshoot and it will oscillate. So this is something that is seen in the 2-point correlation function of the cosmic microwave background. You basically take 2 points in the sky, so let's say here and here, so any 2 points on the sky, and which are separated by an angle theta. Okay. Now the theta is inversely proportional to the multipole number. So this is 1 over L, roughly speaking, and that is what is shown here. Okay. So small values of L, so this is L of 200. This roughly corresponds to 2 degrees, as you can see. This is angle. And large values of L, let's say here it's 2000, that corresponds to very small angles, so small theta. So you can see that there is a peak, at something like 2 degrees. There is no peak before that, and there are lots of peaks after 2 degrees, but eventually the 2-point correlation function is dropping. What does this tell you? It basically says that, okay, if I take any 2 points separated by an angle theta, how likely is it that both of them are at a very big peak or a very big tip? This chance of having a big correlation between 2 peaks does not exist beyond some angular scale correspond to 2 degrees. So there is no angular scale above 2 degrees above which there is a significant peak. There is no peak here. Why? Because from the Big Bang until the time that this wave stopped moving, sound could have only traveled up to some distance, corresponding to this angular scale multiplied by the distance to the last scattering surface. And that's the sound horizon. And we'll tell you more about this later. And then these peaks at larger L or smaller angular scales correspond to, waves that have traveled smaller distances on the last scattering surface. The size of the third peak, this peak, this third peak, it increases, if there is more dark matter. So the fact that we have measured all these peaks allows us to measure how much dark matter there is. Also, the slope of this last part, that depends on how much dark matter there is. Basically, if you add more dark matter, photons cannot leak or diffuse out of small gravitational waves, and therefore power drops less steeply. So using the properties and the features of this CMB spectrum, that there is dark matter and how much of it is there. This is actually the strongest evidence for dark matter in my opinion, because this is the dark matter at the cosmological scale, not in galaxies or galaxy clusters, not locally. We are talking about dark matter that's almost uniformly spread over our entire visible universe. And not only do we know that it is there, we know how much of it is there. And the physics that describes this is very simple. It's the physics of harmonic oscillators, forced damped harmonic oscillators. So it's very easy to understand physics. There is nothing complicated here. We don't have to worry about what stars are doing, what supernovae are doing. There's no complicated astrophysics that goes on here. So this is the evidence that I truly believe. Okay, so this I have already explained to you. I'll go in more detail later. Okay, so the fifth line of evidence for dark matter is that you can measure, just like the 2-point correlation function of photon temperatures in the sky, you can also measure the 2-point correlation function of positions of galaxies. So this is just showing you where the galaxies are. So this is some wedges of the sky where each colored dot tells you that there is a galaxy there. Now you see there is this almost filamentary, net-like structure formed by galaxies and galaxy clusters. The fact that these things exist are already a proof that there must be something like dark matter. So let me try to argue that. The rough argument goes something like this, that until the point that the universe was matter dominated. Early in the universe, there was only radiation, everything was relativistic. Only when the universe became matter dominated could density fluctuations, delta rho by rho, grow after matter radiation equality. Okay, so this is fine. And how do these things grow? These things grow proportional to the scale factor. Okay? Again, if you are not familiar with basic cosmology, don't worry. Right now, I'm just telling you a story. In next lecture, I will give you a little bit more mathematical proof of these things. But this object, delta, grows as the scale factor. So delta of matter, let's say, grows as the scale factor, A. Now, between matter radiation equality and now, this growth factor could have been at most a factor of 1,000. A by A equality. A now is by convention 1 and A equality, we can write it as Z 1 plus Z equality by 1 plus Z today, so which is something like 1100 by 1 or something. So that's roughly 1,000. So this can grow at most by a factor of 1,000. But delta rho by rho, what did I tell you? That the largest delta rho by rho that I had in the early universe at the time of CMB, for example, was 10 to the power minus 4. So delta was max was 10 to the minus 4 at the time of CMB. But it's growing up to a factor of 1,000 more. So it can go at most to a size 0.1, right? But these structures that we see correspond to density fluctuations that are significantly larger than that, so larger than 1 for sure. Okay. So this to be compared with delta of, let's say, clusters, which is greater than 1. So this conflict can only be resolved if already at the time of matter radiation equality there existed gravitational potentials which were larger than this value in their density contrast, and the baryons and the photons forming these galaxies, they just fell into those potential waves. So what is this pre-existing gravitational potential coming from? It is coming from dark matter. So if you plug in the correct amount of dark matter inferred from this story, which corresponds to, in our units now, omega h square of 0.12. If you use that amount of dark matter, you can then show that this conflict goes away. That the amount of structure that you see today in the universe is completely explained by the fact that there was omega h square of dark matter of the order of 0.12. So this is the fifth line of evidence for dark matter. Okay, so let me just summarize this part. There are 5 important reasons why we believe that there must be dark matter. These evidence come from different scales in the universe, length scales in the universe, correspond to totally different astrophysical objects, very different kinds of physics, though all roughly boiling down to F equal to ma in the end. I told you about velocity dispersions of clusters, rotation curves of galaxies. So that was 1, 2, lensing caused by galaxy clusters, features of the CMB, and finally, large scale structure. These are the evidence for dark matter. There is something else called dark energy, which I will not talk about, but just mentioning that this is not dark matter. Although people use matter is energy and all these things equal to mc square, dark energy is a confusing term. You should not confuse dark energy with dark matter, but it is some extra ingredient in our cosmology. Including that, what we now know is that about 68 or 70% of our universe is this thing called dark energy. About 27% is dark matter, and the rest 4% is comprised of ordinary matter, atoms and light. Okay. So this is what our universe is made of. So what we have established so far is that dark matter exists, and I hope you will all agree with it. So at this point, I can take any questions about this first part.
So to all the participants, I mean, if any of you have any query, and please either raise your hand or write in the chat box, or I mean, if you really like, you can unmute yourself and then you can also speak.
Please, I also encourage you to interrupt me in the middle. So I would prefer that, in fact, rather than questions at the end.
Basu, so there is a question from Antarip Gogoi.
Mm-hmm.
He asked why specifically the third peak in the CMB tells us the dark matter density. So I think he's asking why not second, why third, maybe something like that.
It's a good question. Answer is unfortunately a little technical. I will try to give an answer. See, the first peak depends on the total amount of matter, because that determines how large the height of the first peak depends on the total amount of matter. Actually, all peaks depend on everything. It's not that only the third peak depends on dark matter, but we are trying to find that some feature which is less influenced by other things. For example, the position of the first peak is very strongly dependent on the fact that there is a cosmological constant or there is dark energy. It determines the geometry of the universe. You know, what does this angle even mean? That is determined by dark energy. The height of the first peak is determined by how much matter there is, because that determines how large are the density fluctuations overall. You know, all matter, not just dark matter. Now, the third peak corresponds to the case where there is some part of the matter that's falling in, you know, let's say, okay, so let's put it this way, that dark matter, you see, only will have gravitational attraction, but it does not react back to radiation pressure. Radiation does not push dark matter, but it pushes ordinary matter. This asymmetry in the behavior of dark matter with, you know, relative to what ordinary baryonic matter will do, this is most intimately tied to the odd peaks. Now, the first odd peak is this one, but that depends on all matter. So the first non-trivial odd peak is this third peak. And that's why I said third peak determines whether there is more or less dark matter. So that's the rough answer. If you want to know more, I highly recommend that you look at Wayne Hu's tutorial. Okay.
So, Basu, yeah. if I can take the next question.
Yes, please.
It says that I'm not sure which part he refers, but Siddharth Dwivedi tells that what is the frame of reference in which the velocity curves are plotted? I believe when you're talking about the rotation curve, that's what he mentions.
Okay. What is the frame of reference in which
the velocity curves are plotted? That is posted at 10:17 a.m.
Yeah. So what are plotted here are Doppler velocities. Okay, so these are shifts. You know, so suppose I know that that the frequency of some particular line is supposed to be some 100 hertz or whatever number that is. And I see that that particular line is shifted by some delta nu, which is the frequency. This delta nu, I can translate it to a velocity. This is the velocity. This is just an observational velocity that is just being plotted. Now there's a spectroscope sitting on Earth looking at the Andromeda galaxy, let's say, and I'm plotting it in the Earth reference frame.
Okay. So then there is a question from Anuprana who asks that, does this peaks also tells us something about the origin of dark matter?
So now I think this question is back to the CMB.
Yeah, I believe, yes, I believe that's what it is.
Okay, so the question, a very good question. The question is that, do these CMB peaks also tell us about the origin of dark matter? Now, I believe by origin you mean how was dark matter produced? And the answer is yes, but you will have to wait for tomorrow's lecture for me to come to that. Any other questions?
Yeah. So yes. So there is a Fazlu. So I request all the participants to put up their full name, because when they log in, that would be easier for us to identify. So there is someone called Fazlu asked that, can you please explain why damping in small scale is more for less dark matter? So in the same plot that you are seeing in the screen. Yeah, you have only more dark matter, less dark matter in the high multiple. I think he's looking for some explanation along that.
The idea is that suppose this is the density fluctuations in the early universe at some small scale, theta is small. Now, photons that are here can go here, photons that are here can come here and lead to erasing of this density profile, of this density fluctuations like this. If this distance, this distance is comparable or smaller than the distance that the photons can travel. Now, if the photons are being kept there because of baryonic matter, to which photons interact not just gravitationally but also through electromagnetic interactions, they will not travel very far. Okay, but if there is dark matter, they're not interacting with dark matter. On the other hand, dark matter can create much deeper potential wells than baryonic matter. So a combination of these two facts leads to this dependence on amount of dark matter and the amount of damping.
Okay, Naman Bajaj asked you that whether there is any gravitational impact of the dark matter in our planet systems, like motion on the planets.
Not that has been measured. That's a very good question. To the best of my knowledge, there is no evidence for dark matter within the solar system. I mean, it is not to say that there is no dark matter in the solar system. There may well be, but observationally, we have not found any evidence for it yet.
Yeah, hold on. So I'm essentially kind of filtering certain things. So therefore, okay. So there is a question from Aditya Vijay Kumar. He asked that the tail of the CMB correlation function also has fluctuations and isn't merely a slope. I mean, I think the plot that you are referring just now. Yes. Is that physical, and is it produced from the same mechanism as the other peaks?
Absolutely.
Also, how important are the higher L's, at least theoretically, in calculating omega m? Yeah, maybe this is enough. I mean, he has a few more comments, but let's keep that.
So these are all very good questions. And, okay. So it is true that these oscillations that you see here at L's less than 1000, these oscillations continue even at smaller angular scales. There are these oscillations which we are calling fluctuations. Now, one also has to know how well have we measured these fluctuations. Until Planck measured these fluctuations, only I think the first 3 or 4 peaks had been measured very well, maybe 7 peaks or something. But with Planck, the data has gotten a lot better, and there is measurement of even the higher peaks. And it is my understanding that now the determination of omega m depends quite significantly on the fact that you measure the tail of the CMB spectrum. If you did not include that data, your precision on omega matter would actually go down quite a bit. And yes, so the fluctuations are real, and those fluctuations are measured and they matter.
So there is a question. So there are a lot of questions. Ankit Kumar asked, why is there a drop in the rotation velocity of M31?
Mm-hmm.
So okay. Did you show some plot? I probably missed that. Did you probably some rotation curve you have shown
part?
somewhere?
Maybe.
Yes. So he mentioned yes. So he says that why is there a drop in the rotation velocity of M31? So where does he mean? I'm
guess
not sure.
Maybe you mean this part.
Okay,
there is
maybe
a drop there. I mean, other than that, I don't see any other drops.
Yeah.
So
yes.
This has to do with the fact that M31 is a spiral galaxy, and most of the matter in the spiral galaxy. So you see, very close to the center of the galaxy, the rotation curve is dominated by ordinary matter. And the ordinary matter is concentrated in the spiral arms. And in this position, what you have is, you don't have the spiral arm sitting there. It's between two spiral arms, and so you see a drop.
Okay. So Matthew Alex asks you. So Basu, is it fine that if I continue?
Well, we are going to then not. Or would you... We can. I think it's better if we have questions. Yeah.
Okay. So Matthew Alex asks you that if dark matter interacts only gravitationally, could it be accounted as a correction to the Einstein's equations rather than a new form of matter?
Okay, good. So this is, are there other questions that are really important? Because if not, then maybe I will take this one question and answer it in a little bit more detail.
Yeah, just let me just, so there are a lot of questions and I'm trying to kind of filter in a few more. Yeah. Okay, so there is one question from Swapnil. When you spoke of that means just now the radiation domination, you mentioned that the density fluctuations grows like A, I believe. Is that A the Robertson-Walker metric?
Yes, that's the scale factor of the Robertson-Walker metric. Yes.
Yes, I think that is.
I mean, for those who have not followed that part, I apologize. I will tell you about cosmology tomorrow. I'm going a bit slower than I thought I would, but I apologize. Any other urgent question? If not, I would really like to answer that GR question.
Yeah, so you have a couple of minutes, go ahead.
Okay, good, excellent. So let's do that. So there is some evidence for dark matter as we just discussed. So this brings us to this very important question of what the universe is made of. This is a question that we have been asking for maybe 10,000 years. And what is the world around us made of? And one first thing that we would maybe like to ask is that maybe all of this is happening because we are using the wrong laws, that the equation is not F equal to ma, but something slightly different. And that has been tried. And so this is the proposed form. What it leads to is the fact that for accelerations that are very large compared to some number called A0, which I will tell you what it is, F is equal to ma. But for small accelerations, you can imagine that acceleration A goes as v square over r, in the galaxy context. So as you go to larger radii away from the galaxy and v square is becoming constant, A becomes small. So very far out to the edges of the galaxy, A is small, and then they're saying that the F equal to ma law is modified to F is equal to ma square divided by some constant called A0. A0 is some fundamental constant that I will tell you about. Okay. So if you do that, notice something interesting, that ma A is equal to F. This equation, basically says that mass times acceleration, which is a square over a0, if this is equal to gmm by r square. And what is acceleration? Acceleration is v square over r. So m v to the power 4 by a0 r square goes as gmm over r square. Okay, so if r square and r square cancel, this mass cancels, and then what you find, you find is that the velocity becomes a constant. The velocity basically becomes gm a0 to the power 1 over 4. So this is the origin of flat rotation curves in MOND, this modified Newtonian dynamics idea. Now this works in galaxies. It works very beautifully. These are all these different galaxies for which rotation curves are known. And for all of them, there is some flat behavior at the end. There's some scatter. After all, we are doing astrophysics. There is some ordinary matter, observational problems, all sorts of things. But nevertheless, it's a fairly clean pattern that there is a flat rotation curve. And you can relate this v flat, the flat velocity, like this one, with this constant a0, which you can find more or less consistently across all galaxies. This turns out to be a universal constant. So this is the idea of MOND, that there is a new universal constant called a0, which goes into your laws of physics. Instead of F equal to ma, you have to use these laws, and then you can explain rotation curves. Unfortunately, this runs into problems with the bullet cluster, because here we are looking at bending of light around masses, and we can very reliably say that there is mass here and there's mass here, but the galaxies are elsewhere and all the gas is here. So what is all this mass? This mass that I am seeing in lensing, where is it coming from? So no theory of MOND or any of its variants has successfully explained dark matter across all of these different scales. These 5 lines of evidence that I told you about, there is no variant of MOND or correction to GR or anything, which has been looked at in any reasonable detail that explains all the data. Unlike that, just assuming that there is some new material that forms dark matter does explain the data. Of course, what dark matter cannot be is just some planets or neutron stars or white dwarfs or even black holes, because all of this ordinary matter would have melted into a soup at around, let's say, temperatures of 1 mega electron volt or larger, and so they would have shown up in what we would call Big Bang nucleosynthesis data or even the CMB data. So the fact we don't see that, we know that machos or massive astrophysical compact halo objects or things made of baryonic matter, they cannot be dark matter. So there is, as you can see, terms and conditions apply. And one of the things that can be dark matter are primordial black holes, which we will talk about in this workshop a lot. But in some sense, that's not baryonic. That's just a black hole. You can't say that this is made of baryons or whatever. It could be made of anything. But other than that, no known substance can form the dark matter, and MOND cannot give you dark matter. So what we know is that dark matter has no electric charge. It has no baryonic interactions. It has slow speeds at the time of formation, and it is long-lived today. So these are the things that we really know about dark matter. And let me just finish with maybe one last slide, is that all standard model particles, all known particles, violate at least one of these 4 criteria. So for example, if I go, things that are not stable or do not form stable objects, I can throw away. Things that are charged, I can throw away. That leaves only the neutrinos. Forget about the graviton, does not have mass, does not have mass, does not have mass. The 3 neutrinos are the only things that could be dark matter in the standard model. But unfortunately, they are too light. And so they are not slow at the time of their formation. And so they do not give what is known as cold dark matter, which is what we need. So in the standard model, there is no candidate for dark matter. We could talk about this in a little bit more detail, but unfortunately we are out of time.
So Basu,
yeah.
What I have done, there are few more questions I see. I have copied those questions already, and possibly I'll send you by email so that, at the start of tomorrow, you can just make a quick clarification depending on what you think.
I believe we will not have so much time for questions. I mean, otherwise, of course, we have to make some choice whether to cover some material or ask, answer.
Okay, so whatever you like.
What I can offer instead is that I can answer those questions in text.
That's fine. That's fine.
On chat or something.
Yeah, that would be fine. Okay, so then let's thank Basu for his very nice introductory talk. Tomorrow, Basu has one more talk to wrap up the story. So thank Basu. So you can unmute and maybe thank Basu.